So, my name is Erik Rainey. I'm a senior software developer at Amazon. And what I wanted to talk about this morning is something that's, probably a little dated to everyone here about C++14, but I want to at least cover how we can use this in very constrained environments. Somewhat as a follow-on to Bjarne's speech. So if you have technical questions about this, you can always email me. And if you're interested in working with us, you can contact Matt Sigmund, and that'll be in the slides. There's a lot of public information that's been disclosed about Firmware, and I'm not going to get into a lot of details here, but some of the big things are that the drone is actually quite large. It's about 6 feet across. It has 6 motors. It's a hexagonal shape. It does a hybrid VTOL takeoff and landing. And I wanted to show a little clip here. But it does fly over 60 miles an hour at the altitude that we're going to operate at. And what it carries is about less than 5 pounds. And that limits us to a small delivery space, but it's actually quite a large number of catalog items that we can deliver with this mechanism. And the C++14 firmware runs on this drone today. It's not a pipe dream, it's happened. Sorry, the clicker's a little slow. Let's see if it, there we go. So this is the ascent phase. We have a chase drone following it. And as it gets up to speed, the chase drone can't keep up. So that demonstrates a little bit of the hybrid VTOL capability. Lifts up, kind of tilts forward, uses the airfoils to continue flying, and then when it gets to its destination, kind of leans back and does another VTOL. So the outline of what we're going to talk about today is we're going to get into a brief introduction of what firmware is in general, in the environment that the firmware has to operate in. And we'll point out the firmware is not the only thing on the vehicle. There's many, many, many layers to it. This is like the bottom layer in the avionics systems. Then I'll talk about some C++ restrictions we put in ourselves in order to make this work really well, we thought. And some of the recommendations, things that if you're an embedded programmer and you want to use C++14, they're good ideas. Obviously, this is kind of geared toward an embedded audience in that sense. And then we'll talk about how the later specifications, and we'll hand out some reference talks, other CppCon talks that are really good and related to this, and some more information about Firmware if you would like to see that. So as part of this, I want to help level set your expectations because, this is just what we think. A lot of these things are covered in other CppCon talks, and this is not strictly about safety critical guidelines, although that does apply to our situation. So what is firmware? Everyone's got a slightly different take about what firmware is, and there will be a session later this week about what is embedded. And that's somewhat in the same vein. So if you're interested in having a discussion about that, that would be a good thing to go look at. There's a spectrum of complexity in firmware. Things like all the way from your toaster to your router, and everything in between. And these kind of environments also have a bit of a there's many constraint types on how these systems work. There's limited in space, size, complexity, timing. It's not always so obvious what our limits are. And this is, of course, a very broad term used in the category, using the industry across many categories. And as many things embedded, there's lots of caveats and special cases. Whoa. Okay, so usually, although not always, firmware is installed onto the internal memory of a processor. It usually has one execution context, meaning you don't usually have threads, but you can, and plus or interrupt context. It runs as highly privileged on your processor, meaning it's like the kernel. But usually it runs by itself, so there isn't a user mode that goes along with it. It's intentionally difficult to update these because you want them to be hard for people to break into sometimes. Sometimes you want them to be very robust against failures, so it usually is very difficult to update them. And updates, if they do come, are in large images. You update the entire memory space of your program all at once. And you don't do piecemeal updates, usually, but not always. And you have, of course, limited memory space problems. You have limited memory protection mechanisms. So this means that you won't be able to provide a lot of features that you're used to in general programming. There are many types of firmware, and in order of kind of least complexity to the highest complexity, you've got bare metal, and that's usually when you're doing straight assembly or you're doing very, very simple C, and it's very tiny memory spaces that you're dealing with. You have something a little bigger, like SuperLoop firmware, and then you can have something like a real-time operating system. And I make a distinction here because the SuperLoop firmware is not an operating system. And real-time operating systems can be things like FreeRTOS, and things of that nature. Then you can have even something more complex. We have a reduced functionality operating system, and for microcontrollers, this counts as something like micro C Linux. If you've never used micro C Linux, it's a version of a fork of Linux where literally fork works differently than you would expect because it doesn't have an MMU on a microcontroller. And you have larger full operating systems that have somewhat limited flexibility. If you think back to the old Nokia phones, Symbian OS was a C++ operating system, but it had a lot of restrictions put on it when it first came out. And so in my mind, it kind of falls more into the firmware category than a general programming platform. And then you even think about firmware that runs on your home Linux routers that you can install on there. But that starts getting into the complexity levels where you have the ability to update individual parts of your system with apt-gets or dpackages or whatever your particular router firmware uses. So what is the hardware environment that we use for these? This is typically a microcontroller, as I mentioned earlier. And this is kind of like the ARM Cortex-M series. So it's not something that has a lot of horsepower. These classes of devices don't have memory protection. They have no MMU, and that means you don't get virtual memory. But they do have very fast RAM, tightly coupled even, to the core, so you can have one cycle memory accesses. But those tightly coupled memories are very tiny, and you usually want to put something fast in there like your stack. Sometimes other things. It's all up to your system integrator. You have a very small program flash, sometimes a data flash too, but these are usually on the order of those handfuls of megabytes. And the Cortex M series does have an option where you can get them without any floating point, with single precision floating point, or double precision floating point, and it really depends on which chip you bought. And that means that has a side effect of how you compile all of your code with hard float, soft float, single precision, all the different options you can pass to the compiler. And the megahertz ranges of these hardware environments are in the clock speeds, sorry, are in the megahertz range, like tens to hundreds of megahertz, but usually nothing in the gigahertz range. So if you roll your mind back to 20 years ago, this is where desktops were, or even longer than that. And these embedded environments are in that area. They also have, usually, but not always, something called a hardware watchdog. And this is a feature we're going to talk about a little bit later, but I wanted to draw your attention to it now. The watchdog is something you use to prevent runaway actions on your embedded systems. So frequently these systems must interact with lower level buses that are used in various industries like I2C, SM bus, SPI, QSPI, UART, RS-45, CAN, LIN, Ethernet of various types. It's usually almost always, but not always, less than 100 megabits per second. It's time-sensitive Ethernet, EtherCAT. These are kind of industrial standards for Ethernet that give you more deterministic throughput, and they give you more time synchronization across networks. There's many other buses that I wouldn't be able to mention here. That's a whole presentation on itself. These devices typically need to have very fast boot times. If you think about the drone, it has to be able to respond to situations and potentially problems very quickly. So when all these various avionics sensors and whatnot need to boot up, they need to happen immediately. And they need to run for very long periods with no issues. And this kind of applies to a lot of things in industry as well. In firmware, you may have sensors sitting on a tank or a fuel pump that has to run for years without any problems. So that you have to design your software differently when you have that kind of situation. And it may even have ultra low power modes that you have to accommodate when you have these extended run periods. Maybe it wakes up every hour, day, month, year. So your hardware has to be able to accommodate that, and you have to have a good concept of time passage as well. These embedded environments also may support something like ECC memory that you may have heard of in server-side things. But in embedded spaces where you're running apart from the ability to easily service them, ECC in your hardware allows you to detect and correct potentially some amount of errors. And if you have too many, then you may have to take certain actions to prevent bad actions on the part of the firmware. That's a little vague, but there's lots of reasons why you may want to use that. And some of these hardware environments are able to inject errors into the hardware at the hardware level. They have kind of a self-test mode. So if you had the idea, like what happens if my Ethernet controller all of a sudden stops working, I could test that in code in hardware by injecting into the hardware. The hardware itself can kind of self-test. So let's get into the heart of it. What is a SuperLoop firmware, and how is it different than other types of execution environments? Conceptually, it is just a big for loop. It literally is that simple. There is a single execution context. Here, we're not trying to have multi-threaded environments. We are wanting to run a single one. And we'll get to some of the things that might be exceptions to that in a minute. All the executable tasks are visited once in the SuperLoop, and then it repeats. And it just does that forever. And these things are compile time notions. So you may have like a task manager object. It has a run all tasks. It just gets the task list and loops over everything that has an execute interface on it. And those tasks could be peripherals, drivers, services, applications, anything. This means that there's a fixed order which things execute in. And as you can see from the for loop, there's very little else. There's no surrounding logic to do a lot of things. So your task execution cycles, if you were to measure it, may have lots of variability between each iteration. It's not something where you have a time slice in a traditional operating system or some other concurrency ability. Here, we're wanting to make it very simple, very easy to reason, meaning we don't want to, each task may have its own concept of it, whether it's late or early, but the way we'll code these, which we'll talk about later, they're meant to be run constantly, and they check whether or not their ability, their next step is ready. So here in task A, you may have had a lot of work, and then the next cycle, it has very little work because it determined can't do anything. So as I mentioned, there is no software limit of execution time. There is a hardware limit, however. There is no guarantee of when your next start time is using this SuperLoop firmware concept. And blocking constructs in your system effectively block the entire system, except for interrupts. And we chose in this construction not to have an idle task. That's a choice because you could easily insert a task which just causes the whole CPU to sleep. Consequently, if you don't have an idle task, you are always running at 100% processor. So if you have a thermal consideration, you have to handle it all the time. And these kind of processors run in the milliwatt to watt range, and especially on the drone. Your power usage is not so important because you're competing against kilowatt-sized motors, which are orders of magnitude more powerful or more power hungry. But you'd have thermal considerations. If you are running at 100% all the time, you need ability to sink that heat away from the system. Now, how do you collect metrics? Usually you have a trailing window sort of metric on your tasks, and you can measure the minimum in that window or overall time, the average execution, and the maximum over that window overall time of the entire SuperLoop. You could put some timing loops around it so you can get an idea, what is your average SuperLoop time? And when you measure that, you can find out if you are approaching your problem areas, like if your SuperLoop is taking an order of magnitude too long, you have to change the way you've coded all of your system, which is true in many other concurrent applications as well. And you can also measure the per task version like this in the same way, minimums, average, maximums. And they can be implemented with some simple data structures, and you can have a fairly straightforward way of measuring whether or not you're able to address your use case. So what else is missing from this kind of system? Because it's embedded, and I mentioned it's on a microcontroller without an MMU. There are some things that are also missing in this environment that you may be used to. The first one is a choice we made. We have no heap. And that is because this device has to be intensely robust, meaning it has to operate under all conditions, and we have to know our memory usage up front. So when you know your memory usage up front, the amount of times you call malloc and free is just almost non-existent. And because we're on a microcontroller, we have no virtual memory, which means we don't have threads, processes, we don't have a scheduler, because we're a SuperLoop. That also means we don't have a user model. Like there's no way to log into the device and perform system-level actions you may be used to on other firmware platforms like the routers and whatnot. This is more or less complex, but more restricted than those are. And as a consequence, usually you don't have a file system. This is because file systems are notoriously error-prone, as you might know. And there's just lots of points of failure that can come out of file system drivers, the memory allocations you have to do, corruption of the various contents of them. There's lots of checks you have to do. They take a lot of cycles. So typically, if you have the need to have a configuration or something else, you put it into like an EEPROM or something like that that is much more constrained and has better built-in error checking mechanisms. And as a choice we made, we also decided to turn off exceptions. And I'll get to a little bit of why that's the case as well later. And all of the system calls in this kind of environment do not block. They can't because they would, again, block the SuperLoop and then nothing would run. So why is that stuff missing? We want to eliminate entire classes of runtime errors. And this is about becoming more robust, becoming safer in a generic sense. You want to avoid runtime errors that you could detect at compile time. So it's that notion of move a lot of design decisions into compile time and out of runtime. That means we don't get memory fragmentation errors, we don't get runtime out of memory conditions, we don't have thread starvations, priority inversions, priority arrangement issues that are inflicted to us by the scheduler. The SuperLoop, of course, you could still mess that up, right? So it still takes design by engineering to figure out how to write that code correctly. And we'll get into a little bit of that. What are the correct approaches later? Functionality here is kind of your enemy when you are on these very tiny systems, because more functionality means more things can go wrong. And when you're in a constrained environment like this, you want to try to eliminate as much of that as possible. It's much easier to reason about the system when it's this simple. And that means that it's easier to come to a conclusion that you're not meeting your timing, and that in an environment, let's say that you did have threads and heaps and whatnot, you would find out at runtime, where I can find out at compile time, whether or not I'm going to meet my memory requirements. And I can find out at runtime, just like everyone else, that I'm not meeting my timing requirements. This is a much more deterministic way of coding. It's much more repeatable. I can validate that it's doing the right thing easier because I don't have the variability that a scheduler or an operating system may inflict if it's doing background tasks. We've had lots of experience using higher level operating systems that, when it boots up and you're looking for some device to connect to the system and it just doesn't show up for 10 minutes. And then all of a sudden it detects and you couldn't take off for 10 minutes because it just didn't detect that device that was plugged in because the kernel was off doing something else and it just decided not to handle your request. And this reduces, generally, making it simpler like this reduces your testing burden. It means you have to test less things and you have to be less worried about the non-determinism things because they're not there. And it allows you to solve the high-level problems up front because you have to count for failure modes first. And that approach leads you to have to make design decisions about how much memory you're going to use, what are you going to do when you run out of your statically allocated memory. And that makes you generally, well, I guess the best way to say it is it generally makes the code easier to read, easier to reason about, and then you have a better testing story. And you know up front your paths out of your code, your paths into your code, generally just produces easier to reason about code. And undefined behavior, like this removes a lot of undefined behavior as well. You have to consider what happens to your system if your kernel heap is full or if it's over fragmented. What if your kernel gets deadlocked on internal kernel threads? What if your kernel had an exception within the exception handler, right? That happens, and you have to account for that. As Bjorn mentioned, one of the places that has a lot of problems is the least tested path in the error handling code itself. That happens even in these embedded firmwares as well, but it's easier to catch when it's less complex. And what's your option here? You're just going to die? You're going to reset your system? Like, that's not really acceptable in a safety-critical environment. So generally, undefined behavior is not an option. We can't really tolerate it There's not a way to mitigate it, so we have to get rid of it. Especially if you have a certification burden, you have to know how your system is going to behave in all your error cases. You have to design that in upfront. And if you have an open-ended, undefined failure mode, you have to take that out. You just can't tolerate that sort of indeterminism. So what's left in this environment? Many features of the language are still available. C++ has such a strong type system that it lets us be more sure about right behaviors happening as compared to other languages. And we can be far more expressive with our hardware model in C++. And so the language is still able to do a lot for us. And we can use this all the way down to bare metal. We don't have any C left in our code. And we can wrap that last bit. We have to touch assembler functions or built-in functions with good interfaces, because we know we can abstract the notion of maybe the stack pointer, we can abstract the notion of the coprocessor instructions, the cache operations, things like that, in good interfaces. So we can reason about the hardware using these good interfaces and then mock them in our unit tests, all the way down to the bottom. So what is this system like that we have here? Well, we still have a stack, obviously. This is just part of being using a processor that is a von Neumann architecture. There is a normal stack, obviously, but you can also have a privileged stack sometimes in these designs. You still have system calls you can make, and typically we hide dangerous operations behind the system call barrier because it's something that can really mess up the system, like if you have a reboot function. You want to hide it behind the SWI. You don't want people just going out and touching things that they shouldn't accidentally touch if they have a misformatted pointer. Things like logging fatal errors, if you have a data place you can store that in a flash or something. You want to modify your data cache very carefully, because that can lead to all sorts of weird problems. You want to hide that behind your SWI. And if you have keys where you want to hide them from rogue operations that might delete it, accidentally overwrite your keys or something like that, they are usually hidden behind these barriers as well. We still have to handle the vector table and the interrupt handlers. These are things like if you have a hard fault on your bus, or if you have a hard fault, a bus fault, memory management protection errors. There still is something like an MPU where you can protect various regions of memory. And typically we have something like a libc still, but it's one of the very tiny ones, newlib or libnano. And this is intended for embedded processors, which it further restricts your ability to do a lot of system level programming. One of those things is like printf, right? Printf has the ability to do a lot of formatting, but maybe in the version of libc you chose, it doesn't handle floats because you don't have floats on your system. Or maybe it doesn't handle 32-bit support because it's a 64-bit support because it's a 32-bit machine. Usually they'll take out these kind of features to make the size of your new libc or libnano very small. Even these tiny libraries make assumptions about what's available. And one of those that makes assumptions is the SBRK. This was a bug we found in our system when we didn't stub this out. One of our unit test libraries we're putting on the platform decided it was just going to grow the end of memory when we had some extra space in RAM, and it was going to put a heap there. So you have to know all these functions of what they do, and they can be abused in some circumstances, so stub them out. In this environment, you also use a standard cross compiler, but it's a none variety. And that means that something like ARM none EBI, G++, there's very few system assumptions that it makes then. You get to define what your binary looks like, where things are located in RAM, where they're located in flash, what sort of binary formats you support. There are still a few things that does assume, like you still have to have a main. So we have to end up writing our own custom linker scripts, and those linker scripts have to have very strict limits. If you don't have strict limits, you can't move the runtime checks to compile time, because then your compile will just pass and then not flash, and no one will understand why. So in linker scripts, we end up putting assert assumptions about how large the size of certain pieces of memory can grow. If you exceed it, it does not build. And that is the key, like outside of the language. That's one of the keys of asserting that the binary you built is safe in some respects about memory usage. So you can allocate global memory in these environments, but if you put too much in, like in a DMA buffer, it won't build. And this can be not just RAM. You can apply it towards flash. You can apply it towards various other pieces, peripheral memory. You can have lots of different switches. This is not a linker talk, so I'm not going to get into any details about that. But yeah, you can apply this to many sections, like I said. And this moves runtime allocation problems into compile time problems, which is where they should live in a critical environment. So a little more details about the systems. We avoid ISRs. ISRs are interrupt service routines. These are where you get some trigger from the hardware. It says, hey, something happened. The problem is that a lot of hardware allows you to access information only in the ISR. So if you have a bus that you're communicating with and there is an error in the transmission, you only will know that in the ISR. And if you poll for that information, it'll be lost. So there are times you do have to have ISRs. And sometimes you have code that must run within the ISR to keep control loops working. So like motor control is a prime example of something that has to run in ISR because it's a real-time thing, that it's reading positions of the motor and it has to update the control loop to keep it running in parameters. But this means that all the other peripherals that aren't in ISR are polled. And that will lead into some of our execution models later. Generally, global memory space usage is a bad practice in other situations because you can't control who's going to access it. You've got to have a lot of weird protections. But here, it's one of the only things you have. So you use it. Because in the system, we end up creating it such that very little of the global memory is shared. We end up assigning them into individual drivers, pieces. The few of the global symbols end up being like DMA buffers, and they are assigned into your drivers and objects at construction time because they have to be in a separate linker area because that linker area has to be set to be non-cacheable and some other properties that the system has to know about. So there's not really a way to put them in your object. Now the boot path from the reset vector all the way to main is a progression of enabling various layers of feature support for C++. So obviously when you turn on your stack, at some point when you boot, you don't have a stack. And you have to turn that on. It's usually, if not the very first instruction the processor executes, it's very close to the very first instruction. And sometimes your hardware will simply load an address out of a particular spot in memory, and it'll assume that's where you put the stack pointer. Once you have that, or even after you have that, you still don't have globals, which means that you can't just load an object from somewhere. You can't access a table. You can't do anything like that. The only thing you have are values that are encoded in the instruction stream itself. And that means that the very first piece of boot code tends to look like you're casting integers into pointers and storing other integers into them that are usually in hex. And it's very, very messy, but it's all you have. As you build up, you get your CRT0. This is where your standard C runtimes are usually initialized, and from that you get global memory. And now you have a buffer potentially in your global memory that's been initialized. You can start using it, and you don't need to worry so much about, like if you had a global constant that has an address you want to use, you can now access it because it's been read in from the one part of flash into the RAM, and then you're able to do global operations. After that is when your global class constructors get called because you're running before main still. So classes that were in the global space, like a context or an application or a driver, like they'll be instantiated at this point, or not instantiated, constructed at this point. Now, because that happens in a certain order, and these objects are the system, you have to be very sure, and you have to know what is happening in the boot sequence when those objects are created. I didn't mention in any of those previous slide here where the hardware gets turned on, where clocks get enabled, where the clock is accelerated to the full rate, when peripherals are turned on. These are all can be interspersed in all these things, and so you have to know ahead of time. Maybe these objects you're constructing are the things that are supposed to do that. So you have to know what's been enabled in the system at the time of your constructor being called, and you can't make assumptions about that. You have to know whether or not those system calls that you need to make, accessing cache, power control, those sort of things, are they valid yet? If you are the driver of a peripheral, you have to check to see if it's turned on yet. And that means you're going to format a lot of pointers. Hopefully your peripheral has been placed with new already. Can other tasks run when you're in a global constructor? Usually no. Your task loop is not even started yet. So if you're going to depend on someone else, some other driver, like a timer driver, to have started the timer, like maybe it hasn't started yet. And if you're running a peripheral, have the ISRs already been enabled for this peripheral? Are other cores in the system running? If you have a multi-core embedded environment, there are some that do that. Typically, there are some core system features as well that have to be turned on, like the watchdog, the timer, and the pin mux. This is how it controls your GPIOs. Things like selecting a feature. If you have particular buses, as I mentioned, you may select some buses to be on and others to be off. So controlling when construction time happens is very, very useful. So what does our build environment look like? We build from a complete set of binary sources, or source code, into a single binary. All the types are known at compile time. Any unknown types are essentially ignored. So we have protocols that talk in a bus. The protocols have predefined enumerated types and identifiers. If you see a new identifier in the bus, you ignore it. If you want to add that identifier to your build, you rebuild everything. And because these are firmwares, your build takes a few minutes. It's not a big deal to rebuild. So what are the patterns that we find in these kind of environments? In data structures that show up again and again in these environments include things like ring buffers, FIFOs, circular buffers. They're all kind of the same thing. And you see a lot of queues, but the queues can be implemented as ring buffers, and traditionally are. You have a lot of containers that can control when objects are constructed, which is very useful, as I mentioned. You also have custom error code tuple-like objects that may have a result and a cause and a location of an error that you want to capture a problem. And we have an interesting Const expert version of a set of valid combinations of these. And then we can determine at compile time if someone's using like a ridiculous combination of features or values. So like someone wrote that their parameter is busy. Like that doesn't make any sense, so we're going to break the build if that happens. So this allows you to have a better coding policy on your random tuple objects here that report errors in the system. Bus drivers in these environments end up using queues of transactions. And those transactions end up getting scheduled, and then you can detect the status of those transactions and then take actions on them. But they end up having, these queues are ring buffers. The ring buffers are statically sized. So you end up having like a very good controlled amount of memory allocation even for bus drivers. Systems for collecting orthogonal errors, kind of like exceptions, but not really, because you're not necessarily going to throw all the way to the kernel and catch it here. You can combine the error tuple notion and the ring buffer to have a reporting system that will put up these errors into another task, which will capture errors and take actions on them. Rarely are you going to find something where you need to abort or assert and cause a reset in the system, but you can do that as well. So this execution environment ends up dictating that most of your tasks look like a finite state machine or a state chart. There are many good third-party libraries that support this. There's things in Boost for it. There's just a lot of good things. I'm not going to recommend a particular one. But this allows you to abstract your inner logic so they can run in off-target tests, and it's much easier to reason about how a driver or a service or your application works in the first place. And you can get code coverage of all of the state machines and the state charts themselves much easier. So the state charts are always written as non-blocking concurrent because we can't block the system. The process, when we process data in these state charts or in the drivers, we always do them in chunks. We rarely ever process single bytes. So in this polling mechanism I mentioned, if you write a driver and it's just running this in the SuperLoop, processing a byte at a time, you're going to take forever, and you're going to probably miss your timing window. So you want to bulk transfer all of your operations. So like if you're doing SPI or I2C or even UART, especially CAN, you're going to DMA engine drive that. That's your direct memory access engine. You set it up to let the hardware do mem copies for you, essentially into different peripherals. And just as a side note, function recursion is rarely ever used on embedded systems like this because you can overrun the very small stack very quickly, and you can end up with a blocking issue if you don't have a good exit case in your recursion. So it's a rarely used practice. So let's get back to what we do on the drone, because I've been droning on for a while here. So what type of systems use these solutions? These are typically simple bus-to-bus message bridging applications or controllers. So if you think about all of the functions that are in a drone or any kind of real-time system, they're like a graph. They have to talk to each other, and they can either generate data or they can sync data, or they have to go back and forth where they're controlling some external peripheral. So like simple sensors that are a source in this graph topology, like you're reading from an I2C sensor or a SPI sensor, and you're publishing onto something like a CAN bus or an EtherCAT bus. You're a data logger, so you capture all data on a bus or something, log that into an eMMC or something that has a finite amount of memory, but not too huge. Then you can also be a controller, where you're a source and a sink in the graph topology. It's something where you're controlling another device over a UART, controlling a device in a PWM ADC mode, which is like a pulse width modulator and an analog to digital converter, or you're controlling some sort of smart chip over an I2C bus. So at this point, I'm happy to take questions if anyone has them. If not, I can move on to the next section. This is just going to talk about language restrictions that we pose on ourselves. So obviously in this kind of environment, you want to avoid forever while loops. Like there should only be one, and it should be in main, and no one else could ever have a forever while loop. Whenever you do write loops, you have to write them with definite bounds. Without these, you will lead to stuck execution, right? In other environments, you might say, don't ever disable interrupts. It's the same kind of notion. Here, when you're writing your loops, you're always going to put a timeout, or if your timer is not enabled, you're going to put a countdown in there as a fallback. So you're never going to write an unbounded loop. And you got to choose very wisely to use your do whiles, your whiles, and your fors, what's best for the situation. Otherwise, if you do end up sticking execution, the watchdog will cause a reset of your entire system, and you may call them right back. And so if you end up in a perpetual boot loop, you probably coded a blocking call. So pointers. We want to eschew pointers almost entirely. Obviously, being at a system level, you can't, but you want to use references everywhere it's possible. Especially in an MMU-less system, some real memory might exist at 0. Like sometimes these devices have boot ROMs that exist at address 0, so you're not going to cause a bus exception if you access them. Some exceptions We chose not to use exceptions, mainly for space constraint and recursive issues. If you're in an exception handler, C++ exceptions, and something else throws an exception, we don't want to re-enter into the handler to catch that, because that produces a lot of weird problems. We also chose to turn off runtime type info. This is a common thing in embedded applications. We know all our types at compile time, so there's no need for us to do any kind of runtime type deduction. And that also means that we don't use type ID and we don't use dynamic casts. And that's just generally a safe practice, especially in critical systems. You never want to touch dynamic cast. And because of that, of the other mentions about not having a heap, not having virtual memory, we don't use dynamic memory. We don't grow allocations. They are as they are allocated by the static system. But that means that we don't have any news, any deletes in the system, except for placement new. That one's a very useful construct. And consequently, underneath that, there's no malloc and free. And we can tell the compiler, hey, if you ever see a malloc or a free, wrap that call for us, and we're never going to implement that system. So what that means is that if you happen to use something that you weren't sure if you used the heap, and you get a compile error saying, oh, I don't know what wrap malloc is, you didn't define this. That means you touched something that wanted to use the heap and you don't have a heap. So this is your indicator that you're doing something forbidden. And this has the sad effect that many STL types just can't be used. We can't use vector because it's resizable. We can't use unique pointer for the most part, even though it has some nice ways to set allocators. The notion of allocation is what we have to be careful with. And there's also some less obvious ones that if you don't know how these work, you might think, oh, I can make a static bind thing. Well, bind sometimes doesn't use static, and it will try to allocate things. This is one of those areas we found out through many paths that it came down and tried to grow the end of RAM. Many things reallocate memory as needed, and that means that you can't use them in these kind of environments. Even if there is a way to use a subset of the API, it's generally a bad practice. Because when the next engineer comes along, they're like, oh, I've got a vector, I could just do whatever, right? Well, no, and it's not obvious why. And this is a common problem. People try to reinvent another heap with their own custom allocators, claiming that theirs will be static and will be safe, but the interface still fails. If you can return a failure out of an allocator, that itself is the problem, not the algorithm you're using. And we want to remove the notion of, we're trying to remove the notion of allocation, not any specific implementation of that. So when you find a generic programmer who comes into this environment, they go through several stages of heap withdrawal. They don't know how much memory they need at runtime, so they just say they need a heap because they haven't really thought about the memory use conditions, and that's generally a bad sign. Once you convince them that they need to know their worst case memory usage, they say, well, I'll just allocate everything up front, even though technically that can still fail. And when that does fail, because invariably someone else will do their own allocations at runtime, and another driver will get added, and they'll override or over allocate as well, and then your heap fails at boot time. Once you just determine that problem can happen, then you say, well, maybe I'll use a statically allocated pool of memory, fixed sizes, and manage with some bits with an allocated interface. So that's just a heap, right? Don't do that. Okay, so they maybe say, I'll make a enumeration of pre-assigned pool slots, and everyone gets their own pool slot. You can't ever run out. Well, you just re-embedded static memory allocation. So just put that stuff in your objects as you need it, size it appropriately, and check your failure modes. Like don't reinvent heaps when you can't have heaps. This is a very common problem. So this is also a point I wanted to stop. If we have any other questions, if not, we'll move on. So what are our recommendations in these kind of environments? You have to ask the analyzer and the compilers for help. You want to turn on every single warning. You want to have all of them be errors. You want to be as pedantic and as strict as possible, or as practical. Of course, you have to know your compiler. Like if you've got a very specific compiler that you have to use for your environment, you have to know all those flags. You have to know everything that it does. So it's at a system level, this becomes like a burden of knowledge. And if you include third-party libraries, they will fail sometimes under this burden. Because not every third-party library holds to themselves to a very strict warning bar. And they may be problems because they don't have a way to fix them. You may not have a way to fix them. You may have to report problems upstream. And maybe those maintainers don't care about all the flags you turned on. So you have to have a plan about that. Always use your compiler suggestions to improve code quality, because that will, I've rarely ever seen a suggestion that didn't really improve code quality. Compilers today are very good. And even go find every static analyzer you can and turn on even stricter rules. There are a ton of static analyzers out there. Some are free, some are not, and you should run against all of them that you can. These will help find problems in your code that are potentially very, very tricky. So you want to make sure you do that all the time. And where you can, match your cross-compiler and your host compiler versions as closely as possible. This is mainly because if you're turning on all those warning flags and error flags, like if they aren't like right next to each other in versions, one may not support a warning flag over the other, and so you have to have conditions in your build system for it, and that's generally, no one likes that. So along these things, don't reinvent your own basic types. So a lot of people will sometimes reinvent all their basic types. Compiler writers, cross-compiler writers, know better than you when you do that. It's not always true. Oh, it's very rare, but it's not always true that a character is 8 bits. It's not always true that a long is 32 bits. You have to know your platform very well. And generally, if you're going to go and transport addresses around the system, as an embedded system frequently has to do that, you want to make sure you use the standard uint pointer T to transport addresses, because if you're running unit tests on your peripherals, which you should, and that those should run on a host, like your desktop, they can't, if you cast it back to a platform-specific size. You should use the generic size and let the compiler figure it out. So in our environment, we use references everywhere. You try to, pointers have to be rare, but they have to be used, like the stack pointers and the DMA buffers. Those, you can't get away. The hardware wants a pointer, it doesn't want a reference. But they should be really rare. There will be low-level exceptions like vector tables and DMA, like I mentioned. But you can, with great effort, reduce or isolate them, contain them in good interface. And even your hardware peripherals should be references and not pointers. So here we have, like, you get something from the generic context that you may have, get it as a reference. Don't get it as a pointer. Pass something into a function, pass it as a reference. Like this is, I know very basic C stuff or C++ stuff, but this is something you see a lot in code where people will constantly go back to using pointers and having to check those pointers all the time. When you make in place doing your peripherals, make sure you get them as a reference. They can't be null, especially because they're in a hardware address, so why even bother? And when you pass things from a driver into other things, like your timers, pass them as references. If you have a DMA buffer, pass it as a reference. Don't pass it as a pointer. And you should make those things like static arrays. Namespacing. This is a classic problem in embedded programming because people in embedded programming are very much still in the C namespace. Mental frames are very hard to dislodge. This is from a talk. It's also at CppCon. Very good talk. You should watch it. It's at the end of a reference to it at the end here. You have to commit to C++ namespacing, and this is a a problem you see in industry a lot, where they'll kind of halfway name things as classes and enums, but then they'll repeat things all over the place. Like, you really don't want to do this. You want to commit to don't repeat yourself. Keep names simple, don't repeat yourself, scope them properly at the level they're used, and keep the functionality related to peripherals with the peripheral class. So if you have a namespace for a chip or a component or a peripheral, and you have a mode inside of a peripheral, keep it in the peripheral class. Like, don't throw it out in the global namespace. Keep your stuff organized well. And that way, when people see the scoping of things, like it breaks down in a much more sensible way. You want to make a layer cake of your classes. You want to use previrtual functions to have good, clean interfaces. This does come at a cost, but typically this enforces great separation between the details of implementation and your sets of objects. And the virtual overhead is something to keep an eye on if you end up needing like a high performance area, but often design wins and utility of this design wins. And there's not the overhead, though it's non-zero, in some cases, wins over the runtime problem. And if you have a closure where you are building all your source codes, clever compilers may actually get rid of this for you. So in this kind of notion, just have your previrtual foo interface, and you make sure your bar class overrides that, right? It's very simple stuff. But you want to keep it simple. You want to never have a virtual diamond, right? These are things that compilers nowadays stop. They detect it. They can say, hey, you've got this overtly bad behavior. Don't try to make it work. There are ways to secretly make it work. Just don't do that. Especially in embedded spaces, there's no need for hierarchies or models that are this complex. So you may have a foo class at the top that has the interface. You may have bar and baz that both implement foo. And then when you make a GAF, it inherits from both bar and baz. And then when you try to use get count, like, where does that come from? Which one is it? You don't know. Don't do this. You want to use final when it's appropriate, right? This controls what you can and can't subclass, and your customers, which may be other team members, they need to know what's flexible and what is not. Things like a controller, you may have a pure virtual interface for it. When you implement your controller, you make it final. You do not want someone to try to subclass in your controller and then tweaking things and interrupting how things behave. You want to make that final. That's just too dangerous to do. Use resource acquisition at instantiation, or is instantiation, sorry. It's a great practice in general C++ in all circumstances, but it is really essential in embedded C++ because when you placement new things, and you have to destruct manually if you destruct, which most of the time you don't, but when you do, when you do, this mainly, because we don't have a heap, this mainly applies to hardware usage. When you create a driver, the driver is expected to configure a peripheral, enable the peripheral, and when you turn off your deconstruct your driver, you expect your peripheral to be disabled. And then when it comes out, it's like it was never messed with. Right? You want to contain your resource usage inside your class. You don't want it necessarily to be outside. You want to inline only simple methods. This is something that's abused very easily. So you want to have a case where if you are just getting a count, that's a great inline thing. If you're trying to approximate pi from the shape of the moon, don't inline that. That's a little too complex for that. Consting, yeah, this is just so important. You have to const everything. Help inform users about side effects. Side effects are very important in a system level firmware. Like, you have to know whether or not the function is const at the hardware level. So informing your consumers about what is const and what is not const is extremely important. If you have a class here where you have a bar function and you've consted everything, it can get a little wordy, but it's clear that you're processing read-only strings in a read-only section and you're not modifying them. Maybe you're just scanning for something. But you must be clear about side effects using const, because hardware is weird. And hardware doesn't care about the C++ object model. It just does what it does. When you say a method is const, it really has to have no side effects if you're sitting on top of hardware and you're extending hardware. There's things in hardware called read and clear registers, and they, and really what happens is it clears the register after you read it. And this you can't have as const because as soon as you read it, the value changes. Obviously, registers are going to be volatile in some sense, but you need to call out your side effects. And this is a very important system level thing. When you have a wrapping class, you need to remember this on behalf of the hardware because hardware may drop this information. So if you have it's a bit wordy, but if you're simulating a hardware register here, this is the kind of behavior I'm talking about. You may have a status code that returns out of a wrapping class for your register. It will return your value, but then modify it in the hardware. And when you go and ask it the same question twice, like it changes. So that was clearly not a const operation on the hardware. So don't call it that way. And hardware, of course, it has to be listed as volatile. Things that can change on their own accord, you really need to tell the language that it's really volatile. This can have side effects. You may end up having this cascade that reference that you have that's volatile to be handled in volatile methods themselves. And this may cause kind of a rolling domino, not rolling domino, I'll mix my metaphors if I like. But basically this can have side effects, so you need to watch out for that. But listing things as being volatile helps when you have non-native system tests and you're trying to run simulations, and there's a simulation talk about hardware and embedded systems here. This is gonna kind of touch on that sort of notion as well. It avoids weird optimizations that PCs or laptops, if you're running in a unit test, may take because it's thinking, well, you just made a structure in memory. Of course, it's going to behave a certain way, so I can just ignore some behavior. You really need to tell it, no, this is a thing that's very weird. Just treat it as volatile. So in this example, you may have a peripheral register here that has a control, subpart, a mode, and status, but you want to list that peripheral reference as a volatile. When you take it as a volatile and you hold it as a volatile, that's important because when you're reasoning about this at compile time, it will have side effects, and hardware is just weird. So you have to list these sort of things. Mutability is a thing that also happens a lot when you want to avoid it because of that same sort of side effect discussion we had. But sometimes you need it for metrics. Like even in a firmware, you need to collect a lot of metrics. And for locking mechanisms, like even though this is a single thread of execution, if you need to grab a session lock on something like a bus, like you still need to lock it potentially, but you can't block. So you may have a class that has some metric counter. It has to be mutable, even inside of a const thing. That may not be an avoidable thing. Generally, that's up to your use case, but that's a frequent use of it. Or you may have a lock inside of another const method where you have to check a piece of hardware or a bus lock or something like that. And then you may have to make the lock mutable as well. The atomic operator also, the atomic type is very important to share information between your interrupt service routines and your tasks. Critical sections tend to be implemented using atomics. You need to read docs. Atomic has a lot of gotchas, and there's another talk at the end of this I'll reference. These atomics are tricky, and if you don't know your system and how it uses atomics, and how the bus works, and maybe how the bus fetch in the RAM works, they can lead you astray. And as I mentioned earlier, you control your constructors. Static storage definitions can be used, and that allows us to control when objects are constructed. And this allows sequence and lifetimes to be well thought out. Like if we know our system is up and all the device drivers are present, they've been initialized, they've been started, then we can construct maybe our high-level application. And it doesn't need to sit there and wait for all the device drivers to get sorted out. It can just assume everything's been brought up. So we can control when lifetimes stop and start through this mechanism. So you may have in your main function, you may in-place new your application into some aligned storage if your application is named foo here. But if you were to just stack placement on the stack and you're in your main function, and ideally you're never going to leave your main function, so maybe that works out for you too, but now you live on the stack, not in global memory. And your stack is usually kind of tiny, so that could be a problem if you have a lot of buffers in your app. Generally, you want to avoid your pound-defined macros and if-defs as much as possible, and you want to convert them to templates or const experts. This is something that, again, I don't need to tell this crowd but to do it, but people watching online may still use these practices, where you pound define a number of bytes in an array. You really should make that const vector value. You should use a standard array. And don't use debug flags or pound defines for these kind of things anymore. Try to use const experts, static bools, because they can be scope limited. You can't make in C++ 14 the if const expert call, but maybe your compiler does some magic for you anyway. You should look into that. Generally, you want to be as const expert as possible, and you have a simple class. You're going to write a lot of testable assertions using const expert, and you want to use the compiler to test your code. And if you have a lot of anonymous tests in source files, that's the best place to put them, not in headers. You want to ensure also that linker removes from unreferenced code. This is the kind of thing where in embedded cases, you may have like a CRC generator that's a const expert, and it's going to generate the table of fast lookup CRCs, but you're going to put them into an anonymous namespace, generate a bunch of stuff, static assert values, test to make sure it's good. Well, all that happened in the compiler, so I know it's fine. And off I go, and I don't need as many runtime tests as I need before. Well, you can still have them, of course, if you want them, but you don't need them. And of course, static asserting yourself is very important. Do it as much as you can, especially when you're defining hardware peripherals. This lets you assert that the definitions you have are exactly the size that are listed in your data sheets. Things are at the right offsets. Things have the right alignment. So if you have a class that's a structure or peripheral, you assert that it's the exact size the data sheet says it is on this platform you're running on or compiling for. You can also assert that if you did something fancy inside of your structure, that the offsets of those things are exactly where they should be. And you can essentially, previously where you had to just kind of write your struct definition and pray, now you can assert that is exactly how you expect it to be. You know its alignment, you know its offset, you know everything about it. Now you use align as in these situations as well to make sure you understand how the data cache and the bus work. Some of these platforms are just 32-bit, some are 64, some are less than 32-bit. So you have to know how wide some operations you need, how structures used in operations need to be, and where they need to sit in memory to be aligned properly. If you have some sort of SIMD operations you're using, you can still align those to be at the right cache alignment values. That's a very important thing to do. And you can then const for those, so they're not only aligned correctly, they can be const in the system. Strict enumerations are a great thing in these environments to use as well. Enum class is one of the best things in the world, in my opinion. And we can name the exact types they have to be. It's great for peripherals because we then can unpack exactly what should go in those peripheral things. And there's lots of ways to get the underlying type if we need to pull those out to get raw values. So if you have a peripheral, it's got a different bunch of modes that it supports. You can go get the mode of the peripheral or set it directly into the hardware, removing the wrapping type, put it into the hardware with the right value, but you can have it passed into your functions with a strict type so that people can't just throw in random literals. Generally, you want to also delete what you don't need. So if you have a rule of 5 plus 1, that's a very common thing with different objects that are in the system. You want to express your intent to your developers that they can't do certain things with these objects because in this kind of firmware environment, you don't ever want your peripherals, your services, your stack, your applications to be moved around. It's a statically defined system. There's also some additional things you need to worry about when you are getting rid of new and delete in your system, if you use something that internally may trigger additional types of new and delete overloads, the resolution can get confusing. So you may, not always, but you may want to be complete about that and understand your use case. There's a lot of detail in here that you, if you're interested about that, you should look it up because you can end up with a lot of different things you have to delete, and that becomes difficult to maintain. So you really need to know if you're using containers that do fancy allocations, but you're treading that line of I really don't want to have a heap in my system. You have to know that these things end up being used. Deleting them all will help you find out where that problem is happening. Operator overloading is also very useful in these kind of environments where you have static pressure sensors, dynamic pressure sensors, temperatures gauges. But when you use custom types, you want to implement everything in a group. So equals, non-equals, comparisons, math operators, make sure you only do it by scalars in some cases. If you want to make them usable in conditions, operator bool, the not operation, and just generally stay away from the other fancier dereferencers unless you're doing data, in which case use index operator is not a bad idea. But even with the index operator, you need to understand your error case. What if someone accidentally throws in an index beyond your thing? Generally, you make it wrap, but maybe that's not the right case. So you have to figure out your use case. You want to keep it regular. You want to avoid weirdness and unexpected behavior. Obviously, if you have a class foot and it takes a multiply with another foot, that it's kind of wrong. You didn't really want to do that because that creates an area. Don't do that. Generally, it's okay to scale those things, not to just do that. Operator quote is an interesting feature as well that helps make code a little more legible. If you have a silly case here where you're using a furlong, and you can create constant values of furlongs, you can use the quote operator to just create a very easily readable set of delimiters here, and you don't have to just constantly call the constructor all the time. You just use the quote operator. But the trick is you really need to put it inside of a literal space because you don't necessarily want that polluting your global namespace. You want to be intentional about how you use these things. And you want to heed your narrowing warnings. You want to favor the curly braces instead of the parentheses. And this warns about narrowing operations. And that's really important because in hardware, you don't want to accidentally truncate something. That may be a logical error you're hiding if it just silently truncates a value when you really didn't mean that. Generally, you want to be explicit as well on your constructors too. There are some things in the language which may do some additional steps to get you from one point to another. And if you didn't expect that, you want to make sure that your constructors, when you need them to be explicit, and you want to force the code path, that it is only the one code path that you want to allow, because additional steps may be formed. So now we're going to cover a little bit of the later specifications to us, at least. But what is holding firmware back from using these other C++ 17, 20, 23? Well, obviously, the guidelines for embedded programming for critical things, they are not there yet. Misra is now doing its 2020X feedback now, and it's going to take some time to chew on that. AutoStart doesn't cover 17 yet. It's a game of catch-up. The industry has to get experience with these things before they can form opinions about what's safe and what's not safe. So one of the things I'm looking forward to a lot when I get to 17, deprecating, that's very useful. Const exporting conditions, very useful. Variants. These things can be used now, but having them into standard, which means that the guidelines will endorse their usage, is a good thing to have. And having a standard representation of bytes that is endorsed with a standard will be a great thing, because that's a persistent problem. Rarely will we use a fall through, but it is, there are some cases where you might need them. And then moving on to 20, const eval. This is like so great. We absolutely would love to have that in the embedded space, because moving things from runtime to compile time is like the holy grail, right? Module, it's going to help a lot of things. Build times should go way down. You've all seen the talks about this week. It's just a superior way of doing things. Concepts, just like the talk before this, allows you to further lock down your templates. They produce sensible errors. It makes it much easier to read them. And I'm only comparing to C++ 14 here. Braced initializer for bit fields. Like, this is a great thing for embedded people. We've needed this for a while. And of course, if you've seen a lot of the talks about C++ 23 this year, there's a ton of things in the new spec I'm looking forward to for embedded stuff as well. So these are some of the talks, though I wanted people to draw your attention to, because they're really good for embedded approaches, even though they may not strictly be about embedded. And if you want more information about Primary, we have some links here in the slides. More videos, more information about details. So having said that, thank you very much for your time, and I can take questions now. Yeah, if you have questions, please use the mics here.
We have a question online.
Yes, online first.
When using RAII, since you don't have exceptions in your environment, how do you deal with errors occurring in the constructor?
That's a good question. We have that environment ability to report not really exceptions, but just like that error status tuple I was talking about that has like kind of a location and a result and a cause. In the places where things are not reportable, like operators, constructors, void functions that have to stay void, that kind of reporting mechanism we built into our system so that the system can then receive those things, know when they happened, and then take any action they may need to have. So it's kind of like a side channel that basically does the same thing. But in those cases, you may not want to yield execution to an exception handler. You may want to continue and know that, hey, maybe my buffer's not allocated, or it's too busy right now. I allocate, but I'm going to put myself into a different state when I execute. You have to address your failure modes, not always by failing, but by taking a different action sometimes. Question? We'll start over here.
Since you mentioned that you have a very small stack,
yes.
Does your tool chain warn you that you have a recursive function? And the second part of that is, does your tool chain, assuming you don't have any recursion, you should be able to figure out your absolute maximum stack depth. So does it do that for you?
Yes, we turned on the, I forget the name of the flag, but you can ask GCC to set a stack limit and it can figure out the maximum depth in the code because it has the entire code base. And because we don't allow recursion, we can do exactly that. Yeah.
And does it figure out that you have a recursion and tell you that?
I'm not aware. I haven't put that to the test recently. Maybe a couple years ago we tried it.
I imagine that the limit would be unlimited unless you can figure out the termination of the...
Exactly, yeah, yeah. It would really kind of be a halting runtime problem kind of issue, yeah. Go over here.
Hi, my question is about the first loop. It wasn't clear to me like what happens when the tasks run out, or like how does it keep going, or do you add new tasks, or?
Yeah, everything's static. You can't add new tasks.
So they just keep rerunning through the same tasks? That's the semantic?
That's it. Yeah, it just keeps running the same tasks over and over again.
Thank you.
Yeah.
Relatively simple question here. What would be your main reasons to pick C++ over C here? Obviously, there are a lot of great features, but just your top 5 or?
To me, the strong types is like number one. Like having a safer language by a better type checking system produces safer code. And that's, to me, that's just I would never want to be in a less safe language in order to produce safety critical code. There's no reason to do it in my mind. The other features that we have, like controlling construction time, enum classes, I think are just one of the best things in the world. That's really what helps sell me on, and a lot of embedded people on using C++ now. Thank you.
Hi. I was wondering how it works when you have to deal with performance on these devices. Because normally the prime directive when we talk about performance is data locality, optimizing for the cache behavior.
Right.
And now you said you have here a controller where basically everything is in SRAM. So how does it change how you address performance?
Right. So in some parts we can expand on this offline if you want to, but there is a memory protection unit, and you can specify what parts of SRAM are non-cacheable or cacheable, executable, not executable, privilege access or not privilege access, and you can control a little bit of that. And so when you put your stack, for example, you want to put that in your fastest memory possible, and you want to put your DMA buffers in non-cacheable memory so that you don't have to worry about evicting lines or write-through problems. Typically, because you have only two types of RAM, really fast and just slightly less fast, you don't really worry so much about like sorting algorithms, things like that. Usually these embedded devices don't do those things. They really tend to be more data shuttling and using these kind of tightly coupled memories and fast SRAMs, like that's really what it usually ends up doing. Thank you.
Question, do you have a restriction on a single task duration? And if you do, how you handle this?
A restriction on the single task iteration?
Yeah.
Like a start time or a duration time?
You have a task, like you have like an example, how much time all tasks should take. And if one task takes a lot of
yes,
time.
this gets, if I understand your question correctly, this gets into the heart of why you would choose a SuperLoop over a traditional scheduler, right? In these systems, there is no real guarantee, even in a real-time operating system, there is no guarantee your task will actually run when you want it to, because someone can always leave an interrupt turned off, the timer never fires, your task doesn't get, scheduler never puts your task in the front, you can always get starved. You're always playing a game of catch-up and detecting your error. Like you have to make sure when you start your task, I'm at the right time I expected to be at, like I'm meeting my timing deadline, right? If the scheduler is not making that work for you, then you're just adding complexity to the system and you're still having to account for your failure mode. So in a SuperLoop, you still have to account for the failure mode and you design your system more intelligently where, or you design for failure up front. You detect, did my loop start within the time period? If I didn't, I'm gonna set my next time period to be shorter or longer. You're not setting when you're starting, you're just detecting when you are running, which is gonna be the same thing you're gonna do in a traditional scheduler. You're gonna say, I may have requested to start every 4.65 milliseconds because I'm a cell phone, GSM timing loop, but that's no guarantee that you're actually going to hit that. And when you miss it, you still have to account for that. So the code that exists to miss it works in either scenario. Does it make sense?
Hey, I think you touched on this briefly, but I don't completely understand why. Under what conditions do you need to use locks when you only have a single execution context?
That's a great question. Locks are rare in these kind of situations, but they are frequently used when you need to do multiple transactions on a bus that are not a single bundled transaction, and you want to kind of give a remote chip. That chip has some state. You're representing that state in the driver, and the driver may grab the bus and prevent other drivers from accessing the bus while it manipulates that remote chip through multiple stages of some state machine. And then it releases the lock. And in that situation, if multiple drivers are trying to do bus transactions because you have a bus may have multiple chips on it, you want to block session access to those remote chips using that mechanism.
Okay.
Now that could just be a flag, or it could be something as complex as a critical section. It's up to you, the implementer, about which one to use. But they definitely cannot block.
Okay.
Does it make sense? Yeah, no problem.
We have another online question.
Yes.
Since there's such a focus on safety, what reasons do you have to choose C++ over a language like Rust, which reduces risk like undefined behavior?
Yeah, so that's a great question, and it kind of touches on something Bjarne said in his talk as well. A lot of those languages still have unsafe behavior. They just push it down, and they expect the system to kind of handle it for you. We are the system here, so we have to avoid undefined behavior as much as we can, but at the end, we do have to handle it. And there's no way to get around that, really, because the hardware fundamentally is very unsafe. Like a register has no type knowledge of whatever it contains, it just is. So you can take a value off your stack, multiply it by something, stick it in your program counter, take it out of there if you're still running, do all sorts of other weird stuff with it, and it's logical instructions, they're valid, it'll do it, but it doesn't make any sense. So the undefined behavior that the hardware does or can do is just a natural part of life. Specifically with Rust, though, at the time we were evaluating whether to go in the direction of using C++ for this project or with Rust. Rust was this was many years ago, maybe 4 to 5, and only the Rust nightly build was even close to having the functions we needed, and that was just too unstable for us at the time. But Rust is a great language for a lot of those things. I think this one.
Any thoughts on using coroutines to make the state machines easier to write?
Yeah, that is a area of intense interest to me, is how to do coroutines in this kind of environment. My understanding, although it could be completely wrong, is that coroutines require Heap, which means they would not work. But I'm certain that we could implement something that might not use a heap, but it would still be very static, and it still yields a lot of trust to the co-return, co-yield, co-await. Like, you don't know if those are ever going to happen, right? How do you account for a failure mode when you may not ever be called? And so that design notion may itself be antithetical to more of a critical approach to code.
Oh.
I don't know yet.
Okay, I'm still honestly trying to figure out the relation with coroutines and placing them myself, so that might be that answer for the Heap part.
But if anyone knows more about that, please, I would love to hear about it offline. We only have a few more seconds for questions. Yes?
So without a heap, it eliminates a lot of different types of algorithms that you can put on that drone.
Correct.
Are there some?
Well, remember, these are the very low-level avionics pieces. It's not the entire drone. It's just a few components.
Oh, so it's just like the autopilot that controls the flight? Or?
No, these are the sensors, the loggers, the controllers of hardware, not the high-level algorithms that do path planning or any of that.
So you can still have a high-level algorithm that runs on a separate controller that's...
Yes, you can, but as you go into the various certification regimes, they start asking you to remove a lot of those same features. And your high-level computers start looking a lot like this. Because in order to get high certifications, you have to take some of those failure modes out. And One of them is the heap.
So one of the things that I'm working on is pathfinding for drones, and I'm, trying to figure out how would I path from A to B, but there's a lot of limitation there on a low level.
Yes.
And so my question would be like, how would you interact, and have you figured out that maybe some of these pathfinding algorithms have to be done on a pre-planning phase, or maybe outside of the drone and transmitted to the drone?
Well, we can take that offline. Yeah, that's a whole talk in itself.
Okay, thank you.
Not a problem. Next. Oh, same question. All right, great. So I think that's my time. So thank you very much for coming and sitting through this.